always important that we know how to name compounds. We've spent a lot of time in our organic naming, all the way back when we introduced ionic compounds. We learned how to name those, and of course when we looked at simple covalent compounds, we learned how to name those. Before we start naming of the particular compounds, however, let's be sure we're happy with the overall terminology. We have metal cations and ligands. We've already talked about those. Metal cations are the Lewis acids. They want electrons. Ligands are the Lewis bases. They will donate electrons. And we say that that bond is a coordinate bond, a dative bond, a donor bond, however you want to say it. But the ligands coordinate to the metal cations. That's why these are coordination compounds. Now, when we got that whole metal ligand grouping is called complex. It can be a neutral compound when we just call it a complex. It can be a cation, in which case it's a complex cation. It can be an anion, in which case it's a complex anion. Okay. Now, when we're naming, we have to think about the ligand and we have to think about the metal. Okay. We put the ligand name before the metal name. We have to be absolutely sure that we say which oxidation state of the metal it is, because of course transition metals can have multiple oxidation states. And we also need to say how many ligands we have, which we use as a prefix, and the number to name is as one would expect. Di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6. Different, of course, from the organic way of doing things. So let's think of this complex cation here. It's a complex because we've got the metal and ligand together. Metal I'm doing in red, ligand in green. It's a cation because the whole thing has a charge of 3+. The metal is cobalt. The ligand is ammonia, which of course is amine. We have 6 of those, so that's hexaamine. So it's hexaamine cobalt. But then we have to say the oxidation state of the metal, because cobalt could be 2, could be 3, could be 0 as well, but we're not going to hit that in this particular series. So which is it? Well, ammonia is neutral, so that doesn't contribute at all to the charge. So all of this 3+ is due to the cobalt, so it's cobalt 3. So its name is hexaamine cobalt 3. Okay, and that is the name of the complex cation. Now notice there is a difference between how we express it as a name and how we express it as a formula. In the formula, the metal goes first. In the name, the metal goes last. Okay, that also kicks into play. That difference is if we have more than one ligand. You do those alphabetically. Okay, however, if you are in the formula, you always put the anionic ligands first and then the neutral ligands. Again, within the anionic ligands, they would be alphabetical. If you have more than one neutral ligand, it would be alphabetical. So let's consider this species here. We've got 2 ligands. We've got chloride, which of course is chloro, and we have water, which is aqua. Okay. Which is first? Well, aqua, A, comes before chloro, C. We have 2 of each of those, so it's diaqua, dichloro. Okay, and then of course the metal is cobalt, piece of cake. Which oxidation state? Well, we have to think about the overall charge is nothing. So in other words, any anions balance out any cationic part of it. Water, of course, is a neutral ligand, so we ignore that. Chloride is -1. So we got 2 chlorides, that's -2. For the whole thing to balance out, the cobalt must be +2. So it is diaqua for the 2 aquas, dichloro for the 2 chloros, cobalt for the cobalt, and then we just decide it must be cobalt 2. Okay, and notice again the difference between the name and the formula. In the formula, metal first, name, metal last. In the formula, anionic ligands before neutral ligands. In the name, don't worry about whether they're anionic or neutral. We just go alphabetical. A comes before C. And of course, final note, again, water isn't water, it's aqua. Now, if you have an anionic complex, you might remember casting all the way back to when we talked about ionic compounds. Cations, you just used the name. Anions, you had to change the name. So when chlorine atoms became anions, they became chlorides. When sodium atoms became cations, they just became sodium. Okay, so same thing here, and we've got a complex cation, we just name it as is. When we got a complex anion, we add 8 to the end of the metal name. And obviously, if it's nickel, it's nickelate, chromium, chromate, copper becomes cuprate, iron becomes ferrate, gold aurate and silver argentate, just to make it fun. So let's think about this one. Well, we've got a nickel and we've got bromines, bromides. Those become bromo. We've got 4 of them. So we've got tetrabromo we're going to put in first. Then we have nickel. Okay, now let's think about the oxidation state of the nickel. Well, the whole complex is 2 minus. The bromides are each -1, so that's -4. So to turn -4 to -2, the nickel must be +2. So tetrabromo, nickel 2, except the whole thing's anionic, so it's not nickel, it's nickelate. Well, tetrabromo, Br4, nickelate, because it's an anion of nickel, and nickel 2. Let's do another one just for fun. Cu Br4 2 minus. Well, in that case, of course, we're using the funky names. It's still 4 bromines, tetrabromo. It's still anions, so the metal is going to have an 8. We've still got 2 minus, 4 minus from the ligands, so the metal copper will be copper 2. So that becomes tetrabromo cuprate 2. I'm not going to dwell on the naming. There's ones in the quizzes for you to practice. And as we're going through and we're looking at various complexes, if there's something funky about the names, I'll point it out. Before we move on to more detailed discussions of structures and electronic issues associated with coordination complexes, it's worth just throwing out a little bit more terminology at you. First of all, we'll think of a fairly straightforward species. Okay, I'm directly saying what we got here. We've got a cation and we got the anions here. The cation is one we've already seen before. It is a cobalt bonded to the 6 nitrogens of the ammonia, so it's hexaamine cobalt 3, and we know in this case that it's cobalt 3+ because we're told we have these 3 chlorides to balance out. The structure of that would be the cobalt with the 6 ammonias around it, octahedral, if you think back to our VSEPR discussion, and the 3 chlorides just serving as counter ions there. Now, important always for a ligand for you to recognize, for you to know what the donor atom is. In this case, of course, with ammonia, it's nitrogen. We also need to be able to distinguish between what of the ligands, possible ligands in there, are bonded directly to the metal. They are described as being in the primary coordination sphere. And then in this case, we have chloride. Sometimes we'll have waters. Sometimes we'll have other species that are associated with the complex, but they're not directly bonded to the metal. We say that in this case, the chlorides are in the secondary coordination sphere. So this is hexaamine cobalt 3 that we named before on the previous slide. Chloride to go along to say, well, our counter ion, our anion that goes with this complex cation is chloride. We don't have to say trichloride because we can already get the charge from the cation from the name. Okay. Now, something that we will talk about in the structure discussion very early on is how many ligands are actually bonded to the metal. Right? What is the coordination number of the metal? In this case, the metal is bonded directly to 6 atoms of these ligands, so coordination number 6. Now, these ligands are, of course, all monodentate ligands. If we'd had instead 3 bidentate ligands, then the coordination number would be 6 still, because it is the number of atoms that the metal is bonded to, how many bonds the metal forms, essentially. Now, things can get rather complicated when we're dealing with coordination complexes because they have various oxidation numbers, various coordination numbers accessible to them that things like sodium chloride don't. So when I write NaCl aqueous, for example, you know I mean we've got sodium ions, we've got chloride ions floating around in the water. When I write CoCl2 aqueous, however, it's a little bit more complicated than that. There are 2 structures that will coexist in the aqueous solution, and in some equilibrium problems one actually looks at going between those 2 complexes. One of those complexes is easy. It is where you have the cobalt directly bonded to 6 water molecules. So oxygen is the donor atom there. Okay, we can name it quite happily, I hope. Hexaaqua cobalt is cobalt 2+. We know in this case is 2+ because we have 2 chlorides to balance it out. Hexaaqua cobalt 2 chloride, coordination number of 6. However, there is also possible in there a tetrahedral species in which the cobalt is bonded to 2 chlorides. So in that case, of course, the donor atom is chlorine, and 2 waters, for which the donor atom is oxygen. We would name this, of course, as the 2 waters, so that's diaqua, 2 chlorides, so that's dichloro, cobalt 2 again. And of course here the coordination number is 4. So very important as we are going through all our considerations that you know what the ligand is, that you know what the metal is, that you know what the oxidation state of the metal is, and that you know what the coordination number of the metal is, that you know which ligands are in the primary coordination sphere, which ligands are in the secondary coordination sphere. With that, we'll leave this particular set of movies and move on to structural considerations.